So we consider one example to check whether a particular scheme is zero stable or not. This is a scheme which has fourth order of approximation and is expected to have fourth order of accuracy, but let's check what it looks like in terms of zero stability. Who wants to check on the board? Do you want to check zero stability property of this method? What you need to know, what you need to do?
You just need to equals to zero the right side.
You just need to consider the left-hand side of this equation. Because on the right-hand side, everything depends on f. And when we are talking about zero stability, f is equal to what? When we are talking about zero stability of any method, we are considering a very simplified problem. U, derivative of u is equal to 0, right? Which means f is equal to what? A 0. F is 0. So in the scheme, only the left-hand side remains. Can you write the characteristic equation for this method? You don't want. Okay. Let me try.
That's this. Maybe I can.
It's not a rocket science. Let's divide it by this term. What we get? What do we get? Cube, right? Plus 4q.
No.
2 is not 2.
You don't want that I mislead you. Why? Okay. So, what are the solutions?
2 and 3.
5. Minus 5. Minus 5 and 1.
1 and 1 and 3. No.
1 and minus 5.
1 and 4.
No, 1.
1 and 5.
Alexander is trying to apply Iliad's theorem as far as we see.
1 and 5, yes.
Right? Right. Minus 5 and 1.
Yes.
Minus 5 and 1. How about zero stability?
No.
No. No zero stability. Yes, no zero stability. Because this theorem gives required and sufficient conditions. Okay, so this is the fact that q ith is lies below 0, below 1. The absolute value of the complex number is below 1 or equal to 1. Only one root is equal to 1 is the necessary condition for zero stability. So it's not zero stable, unfortunately, in spite of its very attractive approximation property, high order approximation accuracy. Okay, but the zero stability is something that's very simple in terms of the equation, the model equation that we are considering. Usually we are solving problems which are much more complicated than that, right? It's good to have a method that doesn't spoil constant solution. But usually we want from our method something more. And something more means another definition of stability and another model problem. The next step in this stability theory is to take an equation. What equation is next in terms of complexity? to the one that we have just considered.
Linear function.
Linear function. Good. So this chapter or this item will be called absolute stability. Absolute stability. So to discuss absolute stability, we need to consider a model equation of this form. With any complex lambda. This is just a number. U of t0, as usual, it is equal to some initial value. So, this has an exact solution. What is the exact solution of this?
O squared.
Really? This
O
is
that-
separable.
O that.
Hmm?
What's like
Okay, and if lambda is a complex number, this can be written in a trigonometric form as follows: multiplied by cosine of what? Or cosine of t by imaginary part of lambda plus I sine of t by the imaginary part of lambda. And we see that if this guy is below zero, is the real part of lambda is below zero, then this solution tends to zero one time and tends to infinity, right? So the case re of lambda is below zero leads to a stable solution. We expect the solution to be stable when this holds true. So, and this is the property of the original model problem. So we want this property to be preserved by our numerical method. Numerical method. 2 stars to preserve the stability property. Okay, so let us formulate our numerical method for this particular case. So let's rewrite this expression 2 stars for this particular case when our right hand side has this form. What we are gonna get? We have the sum in j from 0 to k, alpha j, y n plus 1 minus j equals to what? Tau. And here comes if we are using a linear multi-step method, any linear multi-step method, then this phi function is just a linear combination of the right hand side computed at previous points, previous k points. So j. So we'll have an expression of this form. And if we put everything to the left-hand side, we will get what? We will get the sum by j from 0 to k just put this y n plus 1 minus j outside the brackets. Alpha j minus tau beta j lambda by y n plus 1 minus j. I'll reorder this. Tau and lambda will go to the first place. Because this product is has some special, will have some special meaning. Okay, so as before, and we want this to be equal to 0. This is an equation, a difference equation. As before, we say that since our scheme is linear, the error, the delta vector, will also we also satisfy the same equation. Okay, so we can write delta here instead of y, and delta is the difference between the exact solution of this problem and the disturbed solution. So again, very similarly to how we did it before, for a simpler model problem, we introduce the characteristic polynomial into consideration. Let's write it down without deriving it as we did it before. How the characteristic polynomial will look like, what it will look like. P of q is equal to the sum by j from 0 to k alpha j minus tau alpha beta j multiplied by
q to the power of n plus 1 minus j.
We can put y n plus 1 minus q to the power n plus 1 minus j minus what? Minus k out, as we did it before. And we'll have k minus j in this case, here. Q to the power of k minus j. Okay?
But in this case,
N plus 1 minus j here, when j equals to k, this is the smallest power. This is going to be the smallest power. When j, well, q to the power of n plus 1 minus k is the smallest power in this sequence. Right? And we can put it off the brackets.
But it cannot equal to.
And then in the brackets we'll have q to the power of k, some coefficients by q to the power of k, some coefficients by q to the power of k minus 1, and so on. Okay? Plus.
But is it equal to PQ?
Yeah, I'm just explaining how PQ was derived.
Put it out and delete it. Is equal to 0, but is it equal to PQ?
I think it's because we define PQ by ourselves, so we can just put those u to the power of -1.
As we did before, we search this solution in the following form.
Я вам спрашиваю просто, почему мы тогда PQ не записали, типа, потому что мы вынесли, почему мы это не выбрали?
The same way as we did it in the previous story about the simpler model problem. Because a Q that's outside the brackets, it only adds a solution Q equals to 0. Right? We can add it formally or we can neglect it. It doesn't matter for the next conclusions, for following conclusions. So we say again, it can be formulated as a definition now. If the roots of the characteristic polynomial p of q are all such that qj are less or equal to 1 and if q, what letter did I use last time? Q qi is equal to 1, then the multiplicity is 1. If the roots of the characteristic polynomial are all satisfying this equation, this set of requirements, then the method 2 stars is called absolutely stable. Absolutely stable. Very similar definition. We are just considering a more complicated problem. And you feel that it is a more involved property, right? The absolute stability of a method, because the absolutely stable numerical method ensures that such problem, which is met in many practically important areas, actually, in chemistry, in physics, everywhere. This equation appears everywhere where you have a process which is either similar to explosion of some kind or a degradation of some concentration, for example, in chemistry. If you are running out of some species in your system, chemical system, because of the reaction, then you will have this lambda that's smaller than 0, and this concentration will go down to 0. So it's very important model equation. And if we prove or if we check that our method is absolutely stable, then we make sure that our scheme does not spoil the solution for this particular problem. And it's more involved requirement and conclusion about the numerical method. Let us check the absolute stability for some typical method. Let's consider absolute Euler method. Let's consider the absolute Euler method. Who wants to check? Do you want to check absolute stability of the absolute Euler? Of the explicit Euler? Explicit Euler.
Yes. Oh. Okay, I can.
What's the steps? Oh.
Well, yeah, sure.
So what you are doing, Alexander?
I want to substitute the linear function.
Yeah, you just substitute this function here. We are considering particular model problem.
Oh, okay. So it's equal to.
And we want to check these conditions on the right part of the board. We want to formulate the characteristic polynomial and then check the conditions.
The
So, in which
Yeah,
case
so
can you
we need,
specify when the conditions of the definition are satisfied? When we have absolute stability and when we do not have absolute stability, yes. So 1 plus tau lambda should be below 1. And usually this is written in terms of the, inequality for tau. Because lambda is fixed by our problem and we can only choose tau. So which tau we can choose? No, I don't like the inequality saying that tau is below 0. Probably you are dividing by lambda, right? And since you are dividing by lambda, we are considering the case when lambda is below 0. Right? So you have to change your inequality signs.
okay.
Because lambda
yeah,
is
lambda
below
is
0, when lambda is below 0.
Okay.
So our original problem is stable only when lambda is below 0. Okay? So tau, let's discuss what we get.
We know that lambda below 0, for example, it can be greater than 1.
Minus. I think we lost minus here. Lambda is just some negative number, that's fine. But the minus should remain here. Okay? Do you agree with me regarding minus?
Yes, because I just
Regarding the
skipped the
minus.
sign.
Okay, yes.
That's
And this way you have a positive some positive number on the right, right? But you have an inequality for tau. You cannot make tau as large as you want. You cannot jump with large time steps. This time step must depend on the coefficient before u on the right hand side of your equation. And in many practically interesting cases, this lambda is a pretty large negative number. Meaning that the solution tends to 0 very quickly. Okay? But what means that lambda is a large negative number? It means that the solution looks like this. Okay? So it tends to 0 very quickly. What's wrong with that? It's very, very stable. The solution is very stable. It doesn't want to expand, explode, or anything. right? Physically, the problem is simple. I shouldn't draw it like this. I should draw it like this. But the numerical method that we are using requires that this step is smaller and smaller, and the larger the lambda, the smaller the time step. The more stable the solution of differential problem, the smaller the time step required to reproduce it. Is it a good property of the method? Do you like it? You have a very stable solution.
No, but it will be stable only if we choose the appropriate term.
I mean, let's forget about numerical methods. Let's think only about the solution of the differential problem.
Okay.
Do you like this curve?
Yes.
What's wrong with this? It tends to zero very quickly. Nothing wrong. And now let's switch on numerical methods. We chose the simplest one we can develop.
Okay, so we need to calculate much, but we need to already know. But our method it just goes to zero, but we need to calculate a lot of steps to get the right.
Exactly. You have to iterate with very small time step, and you might never end up. Go into the time you really want to know. Okay, let's then consider another example, which is what? Implicit Euler method. Implicit Euler is what? Ym plus tau multiplied by f of n plus 1 ym plus 1. Do you want to continue? So you just need to replace this f with a particular form of f. You could put everything that depends on y at point n plus 1 to the left-hand side. That's what you're doing. Very good. And you can actually put everything to the left-hand side, because we need to write down the characteristic equation.
This?
Yeah, but it's better to put this guy to the left as well and say that this is equal to 0. Yes, and then you need to formulate the characteristic equation. How the characteristic equation reads. You have to assume that the solution has the form yn is equal to q to the power of n.
Yes, like this.
Yes, q to the power of n plus 1 multiplied by this brackets, q to the power of n. And you take your q to the power of n outside the brackets. Did you find the answer?
I just want to write down that.
That's very interesting, because the method seems to be simple, its formulation is pretty simple, but the properties are pretty attractive for some problems. Not for every problem, but for some problems it has very attractive properties. Yes, and we come up with a condition. Let's discuss this. I think it's enough.
It's enough.
What you've just written is already sufficient for us to discuss. Yes. You want to continue?
Let me continue. Maybe I know. Maybe I know.
But you don't need to continue. You just need to look here
Okay.
at this relation. We can delete anything else. We don't need any more relations. Let's just discuss what we see. If lambda is negative, the denominator here is what? Is positive, and it is more than 1,
Yeah.
right? The denominator is always above 1 when lambda is negative. Because only at time 0 it is exactly equal to 1. But time 0 is our initial point where we have, where we usually have or know the solution. Okay? This relation is always satisfied. Always satisfied, independently of the time step. By the way, you have t here, but you should.
Oh,
It should be tau. It should be tau.
Oh, yes.
I will fix it.
Sorry.
Just to have uniform notation
Yes, yes.
in our discussions. Let's have uniform notation here. So, for lambda below 0, this holds true for any tau. And this means that this method is absolutely stable. So let's recall what's wrong with this method in terms of its implementation and usage. Why we don't use it always. Why we don't always use this method, since it is very stable, it's very good. Why, what prevents us from using it?
Because we need somehow to find y and
Yes, because we don't like this guy. We don't know it, but we need to know it to calculate this function. So we have to iterate. On every time step, we have to run some iterative cycle that will provide us the next value of y. And this is the only bad thing about this method. And you can recall the other steps to solve this problem. And one of the solutions is to use a predictor corrector strategy. So predict this value using an explicit Euler, put it here, and then calculate the result using this expression, right? But the modified version, which is called Hoynes method, by the way, the modified version with explicit Euler here, it is a Hoynes method. It does not have such attractive stability properties. It is also absolutely stable, but there is a condition that we need to satisfy to keep it to keep it stable. Okay, that's our payment that we need to pay for stability. Okay, with this, I'd like to conclude this lecture, today's lecture. If you have questions, please.